the University of Arizona. And can you turn this down a little bit? And I'm joined here tonight by all of my co-organizers, various members of the university, Steward Observatory. So just some logistical things for the show tonight. We will be having 2 talks with a 20-minute intermission in between, as well as a segment of recent astronomy in the news after intermission before the second talk. So as many of you may know, we are right here next to this active train track. It will almost inevitably come by and blow its horn at us, and you will not be able to hear the speaker. So when that happens, any Spacecraft regulars, would you like to tell me what do we do when the train comes by? Raise our glass, toast the train, and say choo-choo.
Choo-choo.
And then wait impatiently for the train to pass so we can hear the speaker again. Borderlands is very kind to let us host this event here, so and make sure as you are going in and getting your drink, make sure to thank your bartender, tip your bartender, all that fun stuff. We are selling merch over here at this table. We only take cash, unfortunately, but if you have cash, you are welcome to come and check us out. And also, we just like to talk to you all, so feel free. I believe that is everything that I need to tell you guys, so without further ado, I'm not going to hold you up anymore. I'm going to hand it over to our first speaker, Azalee Bostroem, who is a postdoc at Steward Observatory, who will be telling us all about the Hubble Space Telescope.
So that was basically everything I was going to say. I want to tell you about the Hubble Space Telescope, but maybe not the way you're most familiar with the Hubble Space Telescope, which is all of the pretty pictures. So I have this picture and one other kind of picture, and everything else is going to be about Hubble. But don't worry, there are pictures, they're just not space pictures. Well, they are space pictures. They're not far space pictures.
That's my bad, sorry.
Do you want to just advance me to the next slide?
Try it now.
Yeah, I'll turn the audio back up a little bit.
Can anyone turn the audio up a little bit more? Yes. Okay, so my first question to you is, what is the front of the Hubble Space Telescope? Give me a 1 finger, a 2 finger, a 3 finger. This isn't an official trivia question, so I just want to know. Yeah, so actually, well, I'm seeing very little audience participation, but the correct answer is 1. This is not the way we're typically used to looking at telescopes, where the narrow end is where you put your eye. The light actually comes in here, and this is a door that closes to block all of the light. This is where all of the instruments and the computers and everything live. These are our solar panel arrays to give the Space Telescope power, and then this is how it communicates with Earth. So a little bit more basics introduction. This is, as I said, the mirror cover. You can actually look inside here. This is where the big primary mirror is. So light comes in and bounces off there, bounces off the secondary, goes to the instruments. Wow, we have our first train already. Let's see how far I can get. Okay, so this is the instrument bay door. It opens. One of the cool things about Hubble is that it's serviceable, which means that if anything goes wrong, if you want to upgrade, you can, and you will see we did. And then this is where all of the instruments live back here. So the idea for a space telescope originated in 1946 when Lyman Spitzer Jr. proposed an extraterrestrial observatory. He said, what if we put a telescope in space? I feel like we're really used to this idea now, but at the time it was a pretty revolutionary idea. And so why? Part of the statement he made, he put out a paper on why you would want to do this. So the first reason to put a telescope in space is that Earth's atmosphere is like looking through water. So just like when you look through the bottom of water, it blurs the images below. When we look through Earth's atmosphere at a star, it blurs the light from the star. And so that makes it really challenging to see. But if we put... Choo-choo!
Choo-choo!
we don't have to worry about this anymore. Now all of that blurring goes away, gets blocked by Earth's atmosphere. So our eyes see basically the wavelengths in this red box, and it's not surprising that most of the light gets through there. So that's why we've developed to be sensitive to that wavelength range. But there's all of this information in the X-ray, the ultraviolet, different band passes in the infrared, where we don't get any light from outside Earth's atmosphere in. So that's another reason, is to be able to observe in, say, the ultraviolet, you need to be above Earth's atmosphere. But I will say, this is a good thing for us, because it would be hard to survive on Earth if we had all of this X-ray and ultraviolet radiation. So we just have to put telescopes in space. Okay, so we talked about the original proposal. These things take time. So the first thing you need to do when you come up with an idea is decide what your science objectives are. So what is going to make this special and revolutionary, and why should it be funded? Then once you come up with that idea, you need to actually get the funding. So in the 1970s, it was funded, and the plan was to launch in 1983, but we all know things don't always go according to launch. So one other thing I'll note is that one of the things that made this possible was the birth of the Space Shuttle program in the 70s. And this is because Hubble actually fits inside the Space Shuttle bay, and then it gets deployed by being lifted out. And Hubble being serviceable, it's serviceable because the space shuttles can go up, they have this grappling hook that they grab onto it with, and then the astronauts can go out. Okay, so there was a new plan. It was supposed to launch in 1986 in October, but in January of 1986, with the Challenger disaster, all space shuttles were grounded. So whenever there's a space shuttle disaster, shuttles are grounded, and then NASA reevaluates, is it safe to go back? And not only is it safe to go back, but is what we're going back for worth the risk? I was just in preparation for this watching a talk by an astronaut, and he does all the risk assessment, and he said going up in the space shuttle, you have about a 1 in 76 chance of failure. So it's not trivial. So 1988, space shuttle flights resumed, and then in 1990, Hubble was launched on the Space Shuttle Discovery. Here's a picture of Discovery at launch. And so April 24th, if you ever want to know when Hubble's birthday is, that's it. I have Hubble-shaped cookie cutters, so I like to bake cookies for Hubble's birthday. So there were 5 instruments on the original launch. There were 3 cameras: the high-speed photometer, the wide-field planetary camera, the faint object camera, and 2 spectrographs: the faint object spectrograph and the Goddard high-resolution spectrograph. And so I'm going to be talking about this camera spectrograph a couple times, so I just wanted to give a quick introduction. A camera produces an image. This is what we're used to seeing. It takes all of the wavelengths in a certain wavelength range, it collapses it down, and we just get this spatial measure of the intensity of light at different places in space. On the other hand, a spectrograph spreads that out. So a prism is a form of spectrograph where you get actually information of intensity at different wavelengths. And so this is an example. This is a slit that was placed right over this massive star, Eta Carina. And then this is the spectrum that came out. And so spectrographs produce spectra. And this is the green, or the shorter wavelength end, and this is the red, or the longer wavelength end. And you can see that there are these different points of higher and lower intensity, and these correspond, it turns out, to different transitions in elements. And so we can identify what elements are somewhere by what the spectrum looks like. So that's why we like both of these things. This gives us all of our pretty pictures, but this gives us a lot of information on like what speed things are moving at, what their composition is, and stuff like that. So this is what we thought we were going to get, this beautiful. So that was a bummer. There was still great science that was done, even with this distortion, but it is really good that Hubble was serviceable, because we were able to go up and repair it in 1993. So this is, I mentioned that these end of 1993, It installed the corrective optics CoStar, and then it installed the first instrument with its own internal corrective optics. So as every subsequent instrument got replaced, they built in their own corrective optics until during servicing mission 4 in 2009, CoStar could be removed and replaced with another instrument. And so that was CoStar, and then the Wide Field Planetary Camera was replaced with the Wide Field Planetary Camera 2. They were creative in their naming. And so this is what the difference is. This is Supernova 1987A. This is before the corrective optics in October of 1993. And then this is what it looked like in January 1994. Give it time. It'll be impressive. You'll know it. I promise. No?
Try it.
So, CoStar made a really big difference. If you don't know Supernova 1987A, this is the supernova. This is a ring around it from material interacting with material that's surrounding the star that exploded. So CoStar made a really big difference. Let me just show you that one more time, because that was a slow burn. So, servicing mission 1 was really important because it gave us Hubble at the resolution that we were expecting it at. So the next servicing mission happened a few years later in February of 1997. This installed the first near-infrared camera, the near-infrared camera and multi-object spectrograph, and the Space Telescope imaging spectrograph. This was 1997, and both of these instruments are still on Hubble, and the Space Telescope imaging spectrograph is still in operation. That's the instrument that I use most often. This is a picture of STIS, the Space Telescope imaging spectrograph, getting installed. So this is the shuttle bay right here. You can see the wings of the shuttle here, and then this is that grappling hook that's holding it and the astronaut in place, and they're servicing it. You can see the solar arrays here, and that these bay doors are open for installing. Servicing mission 3 was special. It happened in 2 parts because in 1998, there are these things called gyroscopes that help Hubble point at exactly the same place for a long time, and they keep it very stable, but it needs at least 3 to operate. It started out with 6, but by 1998 it was down to 3, and they realized that if one more failed, they wouldn't be able to operate anymore. So they split up servicing mission 3. The gyroscopes, let's do that mode. So safe mode is a mode where everything shuts down safely. It can be restarted again, but it just kind of hibernates until you can get to it and fix it. So Hubble went into safe mode. Servicing mission 3A happened in 1999. They replaced the gyroscopes. They replaced some other computer stuff. But then servicing mission 3B, which was kind of the big point of the servicing mission, installed a new camera, the Advanced Camera for Surveys, or ACS. This is also still in operation and has made many of the pictures that you know and love. And so this is a picture of ACS getting installed. Okay, so servicing mission 4 happened in 2009. We have kind of a big jump, 2002 to 2009. This is because it was supposed to happen in 2006, but the Columbia disaster, again, delayed it. So it took time to convince NASA that Hubble was worth repairing and it was worth the risk of life, and there were different mitigation strategies they did. So if you ever look at pictures of servicing mission 4 launch, there's actually 2 shuttles on the launch pad, and one of them is there as a rescue mission, so that if they got into space and they couldn't come back, there's something else could be sent up to rescue them. And that was one of the ways that they brought the risk down to a low enough number that Hubble would let them do it. So we knew this would be the last servicing mission. The space shuttle program was being retired, and so everything was done to try and make Hubble live as long a life as possible. And I would say it's worked pretty well because all the instruments are still going strong. So the Cosmic Origin spectrograph was a new spectrograph that was installed, and the Wide Field Camera 3 was also a new camera that was installed. First time ever, 2 of the instruments were repaired on orbit. The Advanced Camera for Surveys had stopped working in 2007, and STIS had stopped working a little bit of a risk if we started that it could damage the other instruments. So it's up there, it theoretically works, but I think it's not until everything else dies that they'll try and start it up again. And then the Space Telescope imaging spectrograph was successfully repaired and still going strong. So this is a picture of Mike Massimino. You may see him in some other space things. He's been in a couple different movies. This is the repair of Servicing Mission 4. Okay, so that's your brief history of Hubble. I now want to tell you why I think Hubble is so cool. It has been responsible for more than 1.5 million observations. It gathers about 10 terabytes of data per year. That's not huge in today's day and age, but when you think all of this is beamed down from space from something that launched in 1990, I think it's pretty impressive. And the data has been used in over 19,000 scientific papers, so it's a hugely productive machine because papers are how scientists share their scientific ideas with each other. So this is a picture of these papers published per year as a function of time. And so in black or in blue are papers that are based on new observations. And then in orange,
You've got a microphone.
yeah, I know. It's like on and off. I'm fairly loud, but I don't think I'm that loud.
Never trust a radio to do a wire's job.
That's right. Bring back landline telephones, love them.
That sounds good. Okay. There we go. Okay. So I mentioned that this is not done in isolation, but it takes a community to make all of this scientific progress happen. So the scientific community itself writes proposals, so you propose to do something. This then gets anonymously evaluated by a time allocation committee of volunteers who volunteer to read all of these proposals. These proposals are selected, not all of them are selected, and then some of them are, once they're selected, they go to planning and scheduling, so they get scheduled by Space Telescope on the telescope itself. All of the uploading and downloading of the schedule happens at the Goddard Space Flight Center, about an hour away from the Space Telescope Science Institute. This gives us our observations. These observations then go in two directions. They get calibrated and archived, and so this is the archive that I talked about being able to go back and download any observation from. These archived and calibrated observations become papers. These papers inspire future proposals. This process happens every year. In addition, the Space Telescope Science Institute has an Office of Public Outreach. This Office of Public Outreach produces press releases, it produces pictures, it tries to take the complicated science and simplify it or express it in a way that's understandable to people who don't have a PhD in astronomy. And that then gets sent out to the public. So all of the pretty pictures that we're used to looking at are coming from our Office of Public Outreach. This is important because you elect your Congress members fund NASA, and NASA funds this whole process. So all of us rely on each other. So now I want to talk a little bit about Hubble's science and the one key project and why it's named Hubble. So the key project of Hubble was to find the expansion rate of the universe with a 10% error. So there's this big debate about whether the expansion rate was 50 kilometers per second per megaparsec or 100 kilometers per second per megaparsec. The important piece there is that that's a factor of 2 different. And so this expansion rate of the universe is the slope of this plot. This plot was first made by Edwin Hubble in the 1920s, which is why we call it the Hubble Space Telescope. And he plotted up the distance from Earth and then the speed at which things were moving away from us.
And what he noticed was that as things were farther away from Earth, they were moving away from us faster. And this is telling us that the universe was expanding. But the question is, how fast is it expanding? Does this relationship look like this, where, as you get farther away, things are moving faster and faster and faster, and even faster than this? Or does it look like this? And so that's what we were trying to resolve, is like, where is this line on this plot? So this was the goal. In 2001, the key project published its value of Hubble's constant. It turns out it's between the 50 and 100 with a 7% error. So this was our 10% error goal. This is the value. And the Hubble Space Telescope has continued to be used to reduce this error over time. So with all of these instrument upgrades, new capabilities, new scientific ideas for how we can reduce this, every few years a new paper comes out that reduces this error, so that now we're at less than 2% error. And that's a value as of 2022. So we're still making progress with Hubble. Finally, I want to say, how do I fit into this picture? So I worked at the Space Telescope Science Institute from 2009 to 2014. This is where I fit into the timeline of servicing missions. And in fact, my hire was contingent on servicing mission 4 being successful. So I was watching from grad school, hoping that it would be successful so that I could have a job. It was successful. I worked on the cosmic origin spectrograph and the Space Telescope imaging spectrograph. And then I left in 2014. So this is me in the lobby of Space Telescope. This is a model of Hubble. And you can see advertisement for JWST in the background here. So with that, and what I did there was calibration work. So I said pictures of Hubble are not always pretty. This is what they look like when they come down off the telescope. And what the job is of people at Space Telescope is to take this and clean up everything that isn't really on the sky, so that it looks how it would look if you looked up with your eye. So you have all of these little slashes here. There's a bunch of dots here that aren't real. These are coming from the camera. They're coming from high energy particles that are bombarding the camera. And what you can do is you can clean this up. And that's what it'll look like once it's all cleaned up. So one of the things that people at Space Telescope do is they figure out how to do all of this cleaning up. How do you characterize all of those defects and remove them so that when scientists get their images, they can do science on the real scientific astronomical objects and not defects that you've introduced. So with that, I will stop and I'm happy to take any questions. Yeah, so I failed to mention that on my servicing mission 4 slide there was something about deorbiting. Yeah, so one of the things that in recognizing that that there wasn't going to be another servicing mission, the Hubble Space Telescope is actually in orbit around Earth, and its orbit is slowly getting lower and lower and lower. So one of the things that every servicing mission did was it raised the orbit up so that it could stay in orbit longer. But eventually it will crash into Earth. And the idea was that we didn't want that to happen in an uncontrolled way. We wanted it to happen in a controlled way. So they put a little grappling hook on the end of Hubble that a robot could go up and grab and deorbit it in a controlled manner to a location of NASA's choosing.
What is the estimated remaining lifetime of Hubble?
Ooh, what is the estimated remaining lifetime of Hubble? So Hubble doesn't have expendables like JWST where you're worried about keeping things cool. It's functioning until things start to die. Right now, all 4 instruments, the Cosmic Origin Spectrograph, the Advanced Camera for one white dwarf, it's called G191b2b, with the Space Telescope instrument shell modes. And so because I spent 2 years on those, they are near and dear to my heart. But there are a couple supernova spectra that we recently got. Supernova 2022 ACA, we got the earliest far UV spectrum we'd ever gotten. That one I'm pretty excited about. And then there was this exciting one, 2023 IXF that we got UV spectra of that we'd never seen that kind of stuff before. So it's interacting with all kind of material around it, and we hadn't looked at something that early in the ultraviolet. So both of those are kind of exciting for me too.
Thank you so much, Azalee.
So we will now be going on a 20-minute break. It's 8:07, so please return at 8:27. Take a bathroom break, get more beer, tip your bartender, come chat with us at the merch table. We will see you in 20 minutes.
Wait.
I forgot to say, this URL, you can look at what Hubble's observing right now. At any time, you can see what it's observing. So if you're interested, I thought that was a cool thing.
Not that we have any internet right now.
I switched to my phone.
To your seats because we are back with Astronomy in the News, which will be given by Steward postdocs Dana Krolikowski and Jackie Champagne. I'm just going to continue talking here until everybody is settled again and is ready to listen to your fantastic, what is it called? Comedy show? The Comedy Hour.
Thank you. Hi, yes, I'm Dana Krolikowski,
I'm Jackie.
and we hope you're ready for some good news stories.
The clicker helps to have its.
Try it now. There we go.
Okay, great. Okay, so I realized that there are kind of some common themes with my news stories. This is fairly similar to earlier this year in May when I gave a news story, and I started that by saying that if you ask an exoplanet scientist kind of what they care about, chances are you might hear something about finding life, and then you're going to hear something like, oh, blah, 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 we got to look for atmospheres, and we got to look for water. And then I proceeded to give you a news story about a planet's atmosphere, and caveats and why it matters, but also could be not that exciting. Well, get ready for another one just like that, although we are going to spice it up with a little bit of press drama and some flashy headlines, which will be interesting. Maybe aliens. We'll see. Okay, so what happened? So our trendy new telescope, JWST, what it did is it looked at the planet K2-18b. Yes, they all have terrible names like that. And what they did is they looked at this planet as it passed in front of its host star. And so by doing that, you can see the wavelengths of light that are blocked as the planet passes in front, and then you can use that to say something about what is in the planet's atmosphere. And so you do this by a spectrum. This is kind of the bumps and wiggles in this plot on the right. That tells us what molecules are in the atmosphere. So why did they look at K2-18b? Well, it's been in the headlines before. So what it is, it's a planet between the size of Earth and Neptune, and it orbits in the habitable zone of its red dwarf host star. So the first caveat of this story, habitable zone does not mean habitable. It just means that it orbits at the right distance, that the temperature of a rocky planet at that orbit could have liquid water on its surface. But this is not like Earth at all. This is more like Neptune. So habitable, no. Habitable zone, yes. But still, they thought that we should look at it. Previously, actually, almost 4 years ago exactly, I gave a news story at Astronomy on Tap Austin about K2-18b when Hubble was used to find water in its atmosphere. So that was very exciting. So we know that there's water there. But what did JWST find? So some of these bumps and wiggles show that the atmosphere has methane and carbon dioxide. And so why does this matter? Well, this led to kind of the first flashy headline from this paper's press release, where the authors say that the presence of these molecules actually could mean that there is a liquid water ocean on the surface of this planet beneath its very thick atmosphere. So, whoa, I mean, liquid water. I mean, when we talk about looking for life, like that's one of the first things, right? Okay, great, a little flashy, but that wasn't the thing that kind of caused a lot of controversy. The other kind of bigger, more controversial headline was that they found a very tiny, slight hint of evidence for a molecule called dimethyl sulfide, and there's like a little bump there and a little bump there. It's like 2 points. Yeah, squint. Yeah, I know, this is like a galaxy spectrum, I know. I can't make fun of you anymore. So why does that matter? So that molecule on Earth is made by life, by phytoplankton. So of course, every, CNN and all of the news, they're like, oh my God, they found life, this is amazing. But no, not at all. Like I said, habitable zone, not Earth-like. So this has led to some controversy and a lot of conversations amongst astronomers about kind of the best way to present our results and the science that's being done. There's some concern about the science, right? You take an image with James Webb and you turn it into this. You can do that a few different ways. That could affect your results, which would totally change the way that we would interpret this. If there even is an ocean, if there is an ocean, it might be really hot under high pressure, not in any sense of kind of habitable as we would think about it. And then also this kind of couple data point dimethyl sulfide thing is a little eyebrow raising. So there's been some actual conversation now that's happening about, if we were to find a real biosignature in the atmosphere of an exoplanet, how would we disseminate that? And how would we accurately communicate to the public what it actually means? But regardless of any controversy, this is really awesome work. And I think it's just pretty cool that we're even able to be on a stage debating the presence of an atmosphere and what's in it around a habitable zone planet around another star. And so those questions will thankfully keep us, well, not us, but us employed for the near future.
Thank you. Who was the CNN person going off? Was it Chris Cuomo? Oh, that's good. Okay, anyway. Okay. Magnetic fields. Okay, so off the planet thing. Magnetic fields are just one of those things that you have to learn about when you're a physics student. If you studied physics, you know our pain. And you can always tell who's going to end up an astronomer because we're the ones that ignore the magnetism part of electromagnetism because we don't really get it. And so the category of astronomers that deeply understand magnetic fields is reserved for A, people who are theorists and understand a lot more math than I do, and B, people who are really into obscure radio observations. So we're going to talk about category B, and that's what you're seeing on the left here. If you want to feel comfortable and safe, you can look at the infrared one instead. It is a blob, but blame the resolution of this thing, okay? You're looking through water, remember? Anyway, magnetic fields are given off by lots of different astrophysical objects. They can exist in the atmospheres of planets, they can surround stars, and most mysteriously, they can span tens of thousands of light years across a galaxy. We don't actually have a real solid consensus on how they form or what causes them to exist on that kind of spatial scale, but some contenders include the turbulent motion of charged gas particles, violent processes around black holes, polarized dust grains, and shock waves from supernovae. But observing them is a real challenge because it requires polarization, which is a black box to more than a few astronomers, including myself. Okay, but here comes 9009, that's its name, don't know, 9009. And that's that. A galaxy was discovered through a citizen science project called Stargazing Live, a BBC program. The audience was asked to classify millions of galaxies and search for distant contenders, and they found this beautifully gravitationally lensed thing. If the resolution was better, you'd be able to see how the light is being bent. So this is a foreground galaxy, and then the light's actually coming in this ring around there. The galaxy is at redshift 2.6, so this is corresponding to 2.5 billion years after the Big Bang, and by a long shot, this is the single most distant detection of a magnetic field in a galaxy, because we usually can only see them very close by. By close by, I mean like an unfathomably huge order of magnitude in centimeters, because that is how we judge distances in astronomy, but according to some people, that's very close to us. Okay, so how do they actually find the magnetic field? So on the left here, you're seeing an image from ALMA, the Atacama Large Millimeter Array, and this is probing cold carbon dust grains, so it's basically cigarette ash. And so I said something about polarization before in the hopes that you wouldn't ask me what it meant, and I didn't give you any time to ask. But luckily the press release explains it all for you. Okay, so here's what happens. I gotta read this. The dust grains align along the magnetic field, so the light becomes polarized, meaning that it oscillates in one direction rather than randomly. Great. This can be seen in special polarization observations, and this is the box that I like to uncheck when I'm proposing to the telescope to let me use it. They say, do you want polarization? I say, no, absolutely not. Basically, all it means is that there should be a bunch of arrows around here, and all the arrows point in one direction. Yay. Okay. So the reason that this is a cool discovery, I won't keep talking shit about it, this is soon to appear in Nature Astronomy, and the reason that it's interesting is because we don't know when in cosmic history magnetic fields should have started popping up. Like I said, we see them locally. They should have been around for a really long time, but we have absolutely no clue when they should have started popping up. This one is 1,000 times weaker than the magnetic field surrounding Earth, but it is tens of thousands of light years across. It is likely being caused by intense star formation, which kicks up a lot of that cigarette ash that I mentioned, and so that can obscure all of the starlight, and so basically you can only see it at radio wavelengths. So don't get sucked in by the big magnet, and yeah, feast your eyes on that while Danny tells you more about aliens.
Yeah, we're done with aliens. Sorry, yeah, we're done with aliens. Okay, so a lot closer to home. I don't know how many centimeters, but a lot closer. The lunar party got a bit more crowded recently as India became only the 4th country to successfully soft land, so land something on the moon and not crash. Yeah, very exciting. Just last month, on August 23rd, when their Chandrayaan-3 mission successfully landed. So great. And even more exciting is this lander actually landed, it was the first one to ever land at the South Pole of the moon. Okay, so like, great, we have a South Pole, there's a North Pole, there's a whole surface, why does this matter, right? Well, shocker, this all comes back to water. Right, so we know that there's water ice on the moon, and in particular there's a whole bunch of it in regions at the South Pole. And even more than that, choo-choo, I guess? I don't know. So what's extra interesting is that at the South Pole of the moon, because of kind of the tilt of the moon, I'm gonna have to drink choo-choo. Okay, I'll try to keep going. And there's also a bunch of mountains. So the South Pole of the moon is in a lot of shadow. And so because of that, the water ice that's there can last for a really long time. And I mean like really long time. It's been there so long that we can actually use it and its composition to learn about the materials in the early solar system and help us learn about how the Earth-Moon system actually formed. So that's really cool. We've wanted to land at the South Pole for a long time, and this is the first time that it's happened. And the reason why it took so long is those shadows that help the ice stick around also make it really hard to land, because you have to actually like know where the surface is, and if you can't see it, well then you're gonna crash, which is exactly what happened to the second version of this mission that didn't make it. Also, in shadows, there's less solar power, so it's harder to power your instruments. So great. So not only did they touch down, they are doing some really great science. So there's the Vikram lander, which is named in honor of the father of the Indian space program. And that lander has some devices on it that they've actually detected seismic activity. This may be from impacts on the moon, but it could be a moonquake. We know that the moon does have some seismic activity, not a whole lot. But that's really important for understanding kind of what the interior of the moon looks like. And then there's also a rover, Pragyan, right here, not just kind of zipping around looking cute, but also kind of tasting up the soil and seeing what's in, what was that? Thank you. Seeing what's in the lunar soil. And so they actually found sulfur in this soil, which we didn't know was there. I don't actually know why that's interesting, sorry. But I think it's interesting for some reason. We didn't know it was there, so it's cool. Now, even robots on the moon get a little sleepy, and so both the lander and rover actually got put to sleep early this month when the lunar nighttime started, because there is no solar power. But hopefully in the next few days, they will wake back up as the sun rises, although we're a little unsure if it's actually going to happen because it's really, really cold, and they may just never wake up ever again. But hopefully they do, and regardless, this is a really awesome feat, and we got some cool science out of it, and there are many more missions to come to look at the lunar South Pole.
Nice. Okay, this is a fun one, because I wrote it. I'm famous. Thank you. Okay, So I spend most of astronomy in the news highlighting my colleagues' work here at University of Arizona. Sometimes I have to peer out deep into the universe to find some cool astronomy highlights. I said groundbreaking or space-breaking discoveries. Okay, good job, me. But this time, I wrote an article for this site called The Conversation. I'd never heard of it until they asked me to write for it, but it's a nonprofit news organization. They have a bunch of cool topics, but the interesting thing about it is that everything is published under Creative Commons, which means that anyone can republish it, and I mean anyone. So all of a sudden, I saw my name absolutely everywhere. It made it to Yahoo News, it made it to Astronomy Magazine, and most fun is that I found it on the French version of the Atlantico. It had been translated. My last name is Champagne, but I am from New Jersey, so I don't know if they thought I was one of them or what was going on there, but yeah. So anyway, the article is written for a very general audience. And I'm assuming that if you are here, the audience, or you are not necessarily the target audience of this article. So you are here for the exclusive Just for Space Drafts Smart People edition. Okay, so you're looking here at a quasar field. I'll explain that in a second. And you're looking at a spectrum of a galaxy, which I will also explain. And down here, in this glorious resolution, I have said that you can Google my name to read the full story. It's Jacqueline Champagne. Unfortunately, this influencer named Jacqueline Hill put out a champagne eyeshadow palette, so it's hard to find, but it's there. Okay, anyway, I've talked a lot about high redshift galaxy protoclusters. This is my area of expertise, and I love doing that because I don't have to go pretending like I know what a planet is, and when Danny's up here, I'm like, I think you know what a... Don't know. Can't say what a planet is. Like right here? Sure. So a quick recap on what a galaxy protocluster is. So the largest object that become gravitationally bound in the universe is a cluster of galaxies. So this is tens or hundreds of galaxies that are orbiting around a common gravitational center. And before they collapse into that common center, we find these little pockets of overdensities. Basically, we see a higher volume of galaxies than we should if we were to just point the telescope to a random portion of the sky. So we call that a protocluster. And we look for protoclusters so we can learn about what happens to galaxies when they're in really dense environments. They should be like crashing into each other and crazy things can happen, and so I'm really interested in looking at those crazy things. And so separately, we also know a lot about quasars, which are powered by supermassive black holes, and they're so bright that they outshine the light in the entire galaxy. And it should take billions of years for them to grow. A lot of them are a billion times heavier than our sun. That should take a really, really long time to happen. But we see a whole host of them only a couple 100 million years after the Big Bang. And so what's affecting their growth? Does it have to do with the environment it's in? Maybe if there's a bunch of galaxies around it, that there's some special pocket in the universe where something's happening. So my entire reason for existence is, do quasars and galaxies live in special places? I just want to find something that's special, you know? And so that's the goal of the ASPIRE program. That's the team that I'm on here at U of A. And is the single most tortured acronym. Danny's going to really get a kick out of this. Well, he knows because I complain about it all the time. That's okay. It stands for a spectroscopic survey of biased halos in the reionization era. ASPIRE. So I'll let you have fun trying to figure out which acronym letters come from where. It's not where you think. Yep. The B is lowercase, so it's not in there. Anyway, so I take responsibility. I take zero responsibility for naming that. Okay, but so we looked at 25 quasars, about 800 million years after the Big Bang, with the goal of figuring out what kinds of galaxies these quasars live in, so they have a host galaxy, and then what their surrounding neighborhoods look like. And just like that, there's one quasar in particular popped out as this bustling little city. There's like 40 galaxies around there. Just like we had hypothesized, we think they should be special, so that's really fun. And first and foremost, the spectral features that you're seeing here correspond to certain chemical elements. So in particular, these big ones are oxygen and this smaller one is hydrogen. And so those wavelengths match up to a 3D location in space. So that's how you can figure out that the galaxy is actually next to the quasar in real life and not just like close on the image. But using these spectra, we can actually do more. So I'm trying to figure out some more information about the galaxies inside this little protocluster. Do they have a ton more stars than they should? Are those stars older than what we'd expect from theory? Are the galaxies crashing into each other? And so it'll be really interesting to see if any of these properties correlate with their distance from the quasar, which would lend evidence to the fact that the quasar has a direct effect on its environment. all of this to say, this is a metaphor. The title of my thing was something like, Black Holes Grow Up in Bustling Galactic Neighborhoods. I received many emails that were like, I read that quasars grow up in bustling galactic cities. Am I in danger? I live in a bustling city. Is this black hole going to eat me? I swear I got multiple of these. I got a bunch of stuff telling me that Einstein was wrong, E equals MC squared doesn't make sense. I never said that, so I don't know what to tell you. And so that is why you got the exclusive just for Space Draft Smart People edition, because hopefully you understood that it was a metaphor. The end. Thank you.
So you're telling me that black holes don't form in Manhattan? Correct. Thank you so much, Danny and Jackie. So our next speaker will be Steward graduate student Nick Schragal. I have the power to change the slide. Nick will be talking about eclipses, which is very well timed for the annular eclipse that will be happening next month.
All right, let me get situated here. So since humans stood on their two legs, since humans stood upright, it has been a fascination of us. Eclipses have been a fascination of ours. They have the ability, especially solar eclipses, to turn day into night, and lunar eclipses make our moon look like it is bleeding a blood red color. They have been a fascination for so long that ancient humans were documenting these, and they were making records of when and where these were happening. Unfortunately for us, a lot of these records are something that are fairly nebulous. The oldest currently known depiction of an eclipse is found here in Meath County, Ireland. This is one of the Loughborough cairns. On November 30th, 3340 BCE, a near total solar eclipse passed over this area of Ireland. And the ancient peoples of that area decided to make art about it. This is their depiction of that near total solar eclipse in that area, just over 5,000 years ago. A little bit closer to home, in New Mexico, in Chaco Canyon, there is this petroglyph, the Piedra del Sol. This is what we think to be a depiction of a total solar eclipse that occurred roughly 3,000 years ago. And around a similar time, there were documents being made in ancient China, which we have been using to this day to understand Earth. This is one of those documents. This is one of the oracle bones. This is particularly an oracle bone found in the Hopkins collection of Chinese oracle bones in Cambridge University Library. Oracle bones, if you don't know, are ox shoulder blades and the bottom side of turtle shells that have been inscribed with records in ancient China. This is one of them, which describes the lunar eclipse on a specific day in the ancient Chinese calendar. And because of these good records kept by Chinese astronomers, current day astronomers, in particular one Dr. Kevin Pang of Jet Propulsion Laboratory at Caltech, he used some of these oracle bones from Anyang, China, to determine that the Earth's rotation has actually slowed down by 47 milliseconds. Yes, quite a bit, since 1200 BCE. Now, skipping millennia forward into the 1700s, we have people beginning to predict eclipses. In this case, we have the map drawn by Edmund Halley in 1715 of the eclipse for that year. Now, there have been predictions before Halley's eclipse in 1715. There had been predictions previously, but this was the first eclipse where his prediction was actually matched with records afterwards of observations of this eclipse. So this is the first verified good prediction to within about 20 miles of the true path of the eclipse over Great Britain. And because we can now start to predict our eclipses, we could go and observe the eclipses and start to learn something about the moon and the sun. In 1724, an Italian and French astronomer, Giacomo Maralli, determined that this feature out here, the kind of stringy parts outside of the eclipsed sun, are actually a part of the sun. They are not a part of the moon. They're not a piece of our satellite. This is the sun's corona, as the name would later be attributed to it. We can also study the moon by these eclipses. In 1836, Francis Bailey found and described this phenomenon here. During a total solar eclipse, on the limb of the moon, just as it is going in to completely cover the sun, this is a phenomenon that you can see. It is called Bailey's beads. And what you are seeing here is light peeking through the peaks and valleys of the lunar topography just before the eclipse fully covers the sun. Skipping ahead yet another century, in 1919, possibly one of the most foundational observations in cosmology was made using a solar eclipse. This is the Eddington experiment, conducted by Sir Arthur Eddington during the solar eclipse in May of 1919. What he observed was not the solar eclipse itself, but rather stars that surround the sun. He needed this solar eclipse in order to determine whether or not Einstein's general theory of relativity, that was at the time only 4 years old, was correct. And based on his observations, you can see a couple of streaks here that mark some of the stars that Eddington used. These stars were used to determine that yes, in fact, Einstein was right, changing our understanding of the universe forever. Now, I've been talking a lot about eclipses in general, but let's define what an eclipse is. An eclipse happens when the moon transits in front of the sun as we view it from here on Earth. There are two major types of solar eclipses. We have a total solar eclipse as depicted above, and an annular eclipse as depicted below. The difference here is the distance the moon is from the Earth. During a total solar eclipse, the moon is relatively close to Earth, so it is able to cover the entire disk of the sun, completely blocking it out. In an annular eclipse, the moon is a little bit further away. Its orbit is a little bit eccentric, a little bit stretched out. So when the moon is in this further part of its orbit, it doesn't quite cover the entire sun, so we are left with a ring around the sun instead. So these are what these eclipse types look like. Partial eclipses are seen when you don't get a total or annular eclipse. But there is actually one more extremely rare type of eclipse. It is called a hybrid eclipse, and it is a combination of annular eclipse and total solar eclipse. When the moon is right on that edge of being just too big, of being just too small to see, to completely cover the sun, the places on Earth that are further from the sun, mostly at dawn and dusk, will see an annular eclipse because the moon is just a little bit smaller in the sky, whereas those places nearer to noon, where they see the moon a little bit bigger, will see a total solar eclipse. I would be remiss if I didn't mention that there are also lunar eclipses here on Earth, which are much more easy to view since half the world can see them at a time. And those, of course, occur when the moon passes instead behind the Earth, into Earth's umbra, which is tinted red due to light refracting through Earth's atmosphere, red light in particular, refracting through Earth's atmosphere. We again have total and partial eclipses with lunar eclipses, but there is also the penumbral eclipse, which happens when the moon is not quite in the umbra, but the sun is just kind of blocking out a little. The sun is just kind of blocked out a little bit by the Earth. And of course, why don't we see these eclipses every single month? Because the moon's orbit is inclined. It's about 5 degrees inclined to the ecliptic. So it's just enough for the moon to dip underneath the sun and dip over and under the shadow of the Earth every single month, except for 2 times a year, which is coming up next month, when it just so happens that the new moon and full moon phases pass right between the Earth and the sun, giving us our eclipse seasons. So now it is time for some trivia. On average, at any given place on Earth, how often do total solar eclipses happen? Raise your hand if you have an answer. We have 40 years, 400 years, every millennium, or every 10,000 years. I see a hand over here. A, 40 years? That is not correct. It is not 40 years. That is quite often. Anyone else? 400 years. Yes, 400 years. At any single location on Earth, you can expect a total solar eclipse every 400-ish years. That is, of course, on average. So, we can observe a lot of eclipses here on Earth. If you stand in one place and live 400 years, you can see probably 2 of them. But we can also observe eclipses elsewhere in the solar system. This is an image taken by NASA and the Japanese Aerospace Exploration Agency's joint spacecraft called Hinode. Hinode is a sun-observing spacecraft in orbit of Earth, and it observed an annular eclipse in 2022, in October. This eclipse was not viewed as an annular eclipse from here on Earth. On Earth, in Asia, Europe, and Africa, this was only seen as a partial eclipse. Hinode got the special view. We can also see eclipses on other planets. This is a video from NASA's Perseverance rover taken by the Mastcam. This is an eclipse of the sun by Mars's moon, Phobos. And this is real time. This is not a time lapse. Phobos orbits Mars in about 7 or 8 hours, so its eclipses happen in less than a minute.
That's so cool. How cool is that?
This is not a unique phenomenon for Perseverance. Perseverance is the 3rd Mars rover to have seen eclipses on Mars. Opportunity and Curiosity both have imaged solar eclipses just like this during their times on Mars.
That's cool. That is cool.
Further out in the solar system, we can see eclipses. We don't have spacecraft on the outer planets of the solar system, but we can see eclipses happening from here on Earth. These are images taken by the Hubble Space Telescope of Jupiter during 3 different eclipses occurring simultaneously on Jupiter. There are 3 of the Galilean moons in this image. Io is the one up and to the right. There is Callisto, which you can't really tell the difference between Callisto and its shadow, but Callisto is down here, and its shadow is up here. This is Io's shadow, and there's Io. And this shadow down here is Europa's shadow, which you can see coming in as that bright dot at the very bottom. So 3 eclipses at once on Jupiter. In fact, Jupiter can have up to 5 eclipses at once due to the Galilean moons, including Io, Europa, Ganymede, and Callisto, and one other little tiny close-in moon called Amalthea, which not many people know about because it's not very big, but it is the 5th. Continuing the quick tour of the solar system, we have Saturn, which of course has its spectacular ring system, which can have eclipses on it, as seen here on the left by its moon Mimas, the one that looks like the Death Star. And on the right, there is just a beautiful eclipse on the cloud tops of Saturn by its largest moon, Titan. Both of these images were taken by NASA's Cassini mission. And of course, the rings of Saturn also cast their own shadows on the cloud tops as well, as you can see here in this image, also from Cassini. Finishing up this tour, we have the two blue outer planets. This one is Uranus, being eclipsed by its moon Ariel. You can see Ariel as the white dot and its darker shadow on the right. And Neptune. It's kind of hard to see here, so I'll give you some pointers. This is its moon Despina, and you can see this is actually 4 images stacked on top of each other. Despina's shadow can be seen tracking across on the cloud tops of Neptune, and you can kind of see Despina as a little shadow right there. It's kind of hard to see on the projector, but it is there. I would be remiss if I didn't talk about our favorite dwarf planet, Pluto. Pluto will have eclipses. The problem is we've only visited it once, and it's kind of hard to see. So every 124 years, when the orbit of Charon around Pluto lines up with the sun at the right time, there will be some not really spectacular because the moon is quite tiny from Pluto, but there will be eclipses on Pluto during those times, every 124 years. So let's step out of the solar system and go to the stars beyond. This is an animation here from the European Southern Observatory. I hope it will work. Nope, it's not working. Go back. Please work. I'll give it 2 seconds. I know this stays here for a second. It's not working. That's okay. Anyway, there are these things in the universe. There are these things in the universe that are they're much more common than just single stars like our sun. They are called binary stars. And in particular, there are very, very useful arrangements of binary stars called eclipsing binary stars. Stars that pass in front of each other from our perspective here on Earth. And us. From our perspective here on Earth, we see one star passing in front of the other. That gives us an opportunity to study those stars in depth. We are able to determine the radii of those stars and a bunch of other factors, but really one of the most foundational is the radius of both of the stars in the eclipsing binary pair. Outside of just looking at them going in front of each other, we can also take spectroscopic observations of these binary stars. As you can see here, this is a binary star with the spectra of both of the stars illustrated down at the bottom. From this spectrum,
Choo-choo!
Thank you, Union Pacific. So with these spectroscopic observations, we are able to determine the radial velocities of these
I think you can.
Thank you. Okay. So with these spectroscopic observations, we are able to determine the masses of these stars. Another fundamental attribute of stars that helps us understand what stars, how large stars are, how bright they are, and what makes it, and how all those factors, mass, radius, and luminosity, compare how they are all related to one another. Those are foundational. That is core to our foundational understanding of astronomy. So these stars are incredibly important to our study of the universe as a whole. And these are what I work on. I work on eclipsing binary stars, except I don't work on the times when they are passing in front of each other. I work on looking at these stars and studying them when they are not crossing in front of one another, the effects that can have on our observations. And you too can observe an eclipsing binary star for yourself. This is Algol, the Devil Star. It is an eclipsing binary star in the constellation Perseus. And as you can see here, there is a large difference between Algol during its maximum brightness and Algol during eclipse at its minimum. It drops in brightness by about 67%. Wow. It gets incredibly dim, hence the fact that hence why it has the name the Devil Star. It was seen by ancient peoples and mythology cropped up around it. But every roughly 3 days it goes into eclipse. So if you look up on a clear night, you might be able to catch Algol in eclipse. So we can extend our thinking about eclipsing binaries to exoplanets. This is an animation of 3 exoplanets orbiting the same star, and we can see that we can study these exoplanets by the light that they block from their star in eclipse. We can see their different radii. From spectroscopic observations, we can determine their masses, and we can determine quite a bit more by taking taking spectra of them during their transits and looking at what light gets through the planet's atmosphere. I think Danny showed a similar exoplanet spectrum before, but this is a spectrum from NIRSPEC on James Webb Space Telescope. This is the hot Jupiter WASP 39b. And this is the spectrum from its observations. They observed a transit of WASP 39b across its host star, WASP 39, and this is what they found. You can see here, you can't really read it, it's fine. I'll point out the good parts. There are a number of different peaks in this spectrum that correspond to carbon dioxide being present in WASP 39b's atmosphere. There is a spot here that corresponds to sulfur dioxide, a couple of spots over there that correspond to water. And this is really the power of looking at these eclipses of these exoplanets. We can determine what the composition of these exoplanets are based on the light that they block. It is incredible what we can do in astronomy by just looking at the light and the absence of light. And in this case, we go from the 17 and 1800s, looking at eclipses and being able to study our own star, our own moon, and understanding the structure and composition of our sun, to today, where we are using related techniques to study planets around other stars. But let's bring things back to Earth and to current events, because next month there is the annular eclipse happening. This is the track over time of our annular eclipse next month. And the full track you can see here. In particular, in the United States, this is where it is going through. It's going all the way from Oregon down to Texas. And the closest spot where I'll be next month is in Albuquerque, where it is in full angularity. There is, of course, one other eclipse coming up quite soon, in about 7 months. That is the April total solar eclipse, a little bit further away from us here in Arizona. But this is a total solar eclipse, the most spectacular of them all. And it is heading up over the Great Lakes and up across the eastern seaboard, up across the eastern United States as well. So pretty much everybody in the United States is going to have an opportunity to see one or the other, or possibly both of the eclipses, especially if you live in Texas. So you can see here, this is the map of the United States, and my favorite thing about the April upcoming eclipse is that it does go over my hometown of Cleveland, Ohio. So, because I am an astronomer and because I am talking about eclipses, I must give you the recommendations. Do not look directly at the sun, even during eclipse. Don't do it. You will burn your retinas. Don't do it during the annular eclipse. It is still unsafe to look at the sun during the annular eclipse because of that ring of fire around the moon. The only time it is safe to directly observe the sun without protection is during a total solar eclipse, like if you are in totality during April 8th's eclipse. If you want to view the sun for yourself, there are two standards that viewing it can follow. You have your standard paper eclipse glasses, which you want to check to make sure follow ISO standard 12312-2, or you can also use welding glass. If you're into arc welding for some reason, you can use welding glass as long as it conforms to the ANSI standard here, shade 12 or greater. Yeah, you can use either. There is a list on the AAS, the American Astronomical Society's website, of reputable eclipse glasses manufacturers. So please go check that out before you buy. There is a reputable manufacturer here in Tucson. Their name is Lunt. Their name is Lunt Solar Systems. They're, I think, just a little bit north of here, and they manufacture eclipse glasses. I just got mine last week. But yeah, I really hope that you guys get to see the annular eclipse and possibly the total solar eclipse for yourself. If you haven't seen them, they are truly spectacular events. And with that, I will conclude my talk. If you have any questions, please feel free to ask. I think your question, is there any place on Earth where you cannot see an eclipse? The only places I can think of are at the poles when they are at nighttime. That's pretty much it. You could see lunar eclipses from there, but yeah, during the poles during their night times, during their 6-month night times. All right, I don't see any other questions, so thank you all for coming. Oh, one more question. Have I ever seen a total solar eclipse? Yes, I have. I was very lucky to, I did my undergraduate work in Alabama, in northern Alabama, which was very, very close to the 2017 total solar eclipse. We went up to Nashville to go see that, and it is truly spectacular. If you have the chance to go and see an eclipse, absolutely do it. There is nothing on Earth like it.
That's true. Right there.
All right, thank you.
And thank you all for coming. We hope you enjoyed the show. Our next show will be October 17th at 7:30 p.m. And on your way out, make sure to thank and tip your bartender. Feel free to come talk to us after the show. And otherwise, we will see you next month. Thank you.